this is good. Alright, so let's get started. The title of this talk is all about our anatomy of a credit card stealing point of sale malware. So, can I get a show of hands of how many people got their credit cards reissued as because of either Target, Home Depot, Michaels, PF Chang's? I mean, I'm not going to continue because the list from last year is in the dozen. So this is a pretty real problem that is affecting us here in the US more than anywhere else in the world. And what we'll try to do today is quickly go over how this type of attack happens, what is the fundamental flaw, how can this be corrected, and just take a look at what all things that we as customers could do. Another thing is, I have a pretty good demo. I hope the demo guards are with me, and the demo is about the credit card stealing malware. So, quick introduction. My name is Amol. I head the vulnerability labs at Qualys. And okay, so this is the agenda for today. What we'll do is we'll take a quick look at point of sale systems and credit cards. So, a point of sale system, everyone has seen it. It's basically something that when you check out at Walmart or Target or any of these stores, you hand over your credit card to the cashier, or even at 7-Eleven, at the cab that I took today. You hand over your credit card, they do something with it, most probably in the US, swipe it, and they hand you your credit card back. So we'll look at what goes inside that point of sale system, and a little bit more about credit cards, as in different types of credit cards, the ones that we use here in the US, the ones that are more prevalent in Europe and the rest of the world. We'll look at how the attack works, how the attack works. There will be a demo. So this, in this demo, what I've done is I've written a similar point of sale malware that was used in some of the hacks. The reason for doing that was a lot of people have reverse engineered, and there are a lot of blogs already on the malware that was used. So instead of again telling everyone how that particular malware worked, I said, okay, let's try to write such a malware, and if I'm able to do that, then I can sort of explain it better. I can explain better how to protect against it. So it's a homegrown malware. I have a sort of a fully functioning point of sale system here which can accept credit cards, and I may need a volunteer to give their card to me. And then we'll look at some of the countermeasures that we can take a look at. So before getting started though, there is one important information I would like to give you out today. If you are Linux administrators, how many of you are Linux administrators or work with Linux systems? There was a pretty important vulnerability announced today called as the Ghost, and that allows remote unauthenticated attackers to basically take complete control of your system, get root access, shell access. So all the details are available at the Qualys website, laws.qualys.com. We released the advisory today as a coordinated disclosure with all the vendors. So all the vendors have patches available as well this morning. So just something for you guys, for you to take a look so that you don't miss it just because you are at a conference. So go to laws.qualys.com and it has all the details. So let's get back to credit cards. So this is a screenshot from the 2014 Verizon data breach report. And what it shows is in the first column are the POS intrusions, point of sale intrusions. attacks. They have other attacks as well, web application attacks, theft, miscellaneous errors, crimeware. But the POS or point of sale system attacks are pretty significant. And as you can see, the accommodation industry had 75%. Now this is the latest report, 2014 report, but the data that it has is for 2013. So actually this data is 2013 data. When they come up with this report this year, I'm sure accommodation, which was targeted 2 years ago, hotels and all, then you again hand over your credit card to the hotel reception and they swipe it. That was on a large 2 years ago, which is what this 2014 data is. When they release this for 2015, which will have the 2014 data, I'm sure retail, which was only 31%, will be in, I guess, 70s or 80s or even higher, because, I mean, yeah, all these different retailers that we have heard about in the last year. So yes, there is a problem. So let's look at credit cards. Now there is nothing new in credit cards, everyone uses them. There are still some significant differences. So in the US, most of us use these type of cards. So these are magnetic stripe cards, so there is a magnetic stripe there, and there is some data in here. Now this is pretty similar to just a magnetic stripe being pasted on a plastic card. So if you guys remember tapes, like cassette tapes that had like a side A and side B, in the player, you close the thing, you press play, those tapes, and then it had like 2 holes. You know what I mean, right? Come on, all of you are not from the MP3 age. So it is exactly that tape. I mean, of course, not exactly, but yeah, it is pretty much similar to that tape, which is just pasted on a magnetic stripe. And in those tape recorders, there used to be a head, and there used to be 2 holes, and the tape used to slide over the head, by which the head read your songs. In this case, there is a head in this type of a card reader, but of course, there is, since there is nothing moving, you physically swipe it. So instead of what happened in our tape players was that the two circles, the holes in between, they rotated and the tape slide across the head, data got read. Here you swipe the card manually and data gets read. So it's pretty much the same sort of technology that you had on tape, and actually one of the IBM engineers, that's how he sort of invented or sort of did the first credit cards, where he was trying to sort of stick that tape to a plastic card. So anyway, those are the cards that we use mostly in the US. Nowadays, some banks have started issuing these type of cards which have a chip on it. And these cards have been prevalent pretty much in Europe, in some parts of Asia, in India, for a long time now, and they are a lot better at security. They are called as chip and pin cards because there is a chip in here. And what the chip basically does is that it has basically all the cryptography set up so that it's difficult to basically steal information from that card. There is a pin associated with it, so when you swipe a data, I mean, you must know, if you go to like London or Paris, when you swipe the data, when you swipe your card, and if you have a chip and pin card, it will also ask for a pin, just like debit cards here. And the last type of cards are the newer ones, the AFC ones, where you don't have to swipe anything, you don't have to slide anything. So these cards, by the way, you don't need to slide because there is a chip there, and when you put the card, there is a chip reader inside the card. So there is no swiping required because the chip basically is read by the reader. The last type of cards are the newer NFC-based cards, as you sort of just tap the card or you bring the card close enough to the reader and it basically can read data. So most of the attacks or most of the hacks or data thefts that happened in the US last year were the magnetic stripe cards, and that's what we are going to take a look at. So before going through the attack, this is a typical terminal or a POS, point of sale system, nothing really fancy. You usually have like a touchscreen display or something, heat-based printer, a cash register which is sort of hooked up to it so that it opens. There is a magnetic card reader, something similar to this. And by the way, these systems are pretty cheap. So if you go on eBay, you can buy this for like 15 bucks, or I mean, I bought this for like about 15 bucks. So these systems are pretty cheap. You can get them at eBay or any other store, 15-20 bucks. There are some a little bit more fancy ones, but the cheapest one is like 20 bucks. And then last but not least is there is a box here, which is basically the CPU, or it has the operating system for the POS terminal. Now, POS comes in a lot of flavors. There are at least 2-3 dozen leading vendors that can provide you with this. A lot of them still use stock operating systems, so it will use some blend of Linux or some blend of Windows. Or actually, Microsoft has a special operating system called as POS. It used to be with POS OS, but a lot of these vendors use some sort of an embedded Windows or embedded Linux or Microsoft's POS operating system. So just something to note for. So this, the next like 3 or 4 slides are going to be a little busy, a little bit technical, but don't worry too much about that. So this is what the magnetic stripe on our magnetic cards look like. It has 3 tracks, and each track has a certain specification about the width of the track and how much data it can store. So for example, track 1 has 210 bits per inch, and therefore it can store 7 bits per character, so that boils down to 79 alphanumeric characters. So track 1 can store 79 alphanumeric characters. Track 2 has 75 bits per inch, so it can basically store less amount of characters, but it has more, and because it has less bits per inch. Similarly for track 3. So in credit cards, mostly only the track 1 and track 2 are used. Track 3 is used by, thank you. Track 3 is used by hotel cards, or magnetic cards are used at a lot of other places, right, other than credit cards. So hotel cards, or in parking lot, or that type of thing. And this is all public information. In fact, this image was also from some q-card.com. So this is all very public information. So if we look, and now this is where it gets a little bit busy, so please hang on with me. So this is what, let's say, card 1 data looks like. So this is what it looks like. And this is according to the RFC what it should be. So we'll quickly take a look at how the data is stored on the card. And the reason we are diving down into this level of detail is that will help us study how the malware works and just help us understanding these breaches. So on the track 1, so you have your card, you have your magnetic stripe, it has 3 tracks. On the first track, data is stored something like this. And this diagram is the RFC for it. So the first byte is a start sentinel. So it's basically just telling the card reader that, hey, when you get this byte, that means the data starts after this. So when you hit the % sign, or when the card reader reads the data, when you get the % sign, the data is after this. So it's just telling that. That is followed by field separators. So there are various fields. So this is the start of the data, and this is the start of the first field. That's what just this piece is. Then it has your primary account number. That's usually the 19-digit number which is printed on your card. So that is on track 1. Again, a field separator to tell that, okay, now we have a different field. Name on the card, 26, maximum 26 alphanumeric characters. Again, a field separator saying that, okay, now it's a different field. And then this is for additional data. Now, this additional data is basically expiration date, which is 4 characters, service code, which is 3 characters. Service code just says how the card can be used, what is it, a debit card, or like there are these lot of different codes for banks, and that's stored in this 3-digit service code. Followed by discretionary data. Now this, even though it says discretionary data, it contains your CVC or CVV, or the card verification code or card verification value. Now, on your card, on the back side, like if you call someone and give your card, they say, what's your CVV number on the back side? Or if you use your credit card online, it asks you what are these 3 digits behind the card. So this is one of my cards that asks for this. So that is also sometimes called as CVV, but there are actually 2 CVV. So there is one CVV which is on the magnetic stripe, which is called as just CVV. And actually the CVV which is written on the back of the card is CVV2. And both of these numbers are different. And then we'll see why they are different and what's their significance. And then again some field separator or end sentinel saying that, okay, the data is now ending. And then LRC, which we'll again take a look at it in the next slide. So this is track 1 data. Again, no need to really memorize this. It's just some data with some field separators where things are stored. Track 2 data is also similarly like that. It's just that we saw that track 2 has less density per inch, so it can store less data, and we won't go into the details of all this, but it's similar. It has your PAN, it does not have your name, but it has all the other fields. So what are some of the major transaction types? One is the card swipe, and the second is card not present. So card swipe, when the card is physically present, that is the time when the CVV in the magnetic stripe is used, and bank uses that CVV, authorizes your card. When the card is not present, when you buy something online or things like that, then it asks you, basically, first there was no CVV2, there was just the magnetic stripe, and everything was fine. The CVV was on the magnetic stripe, and it was not on the card anywhere. So when you swipe, that was sent to the bank. Bank said, okay, credit card number, name, CVV, all matches, authorized. Now what happened was with online banking and e-commerce, the card cannot be swiped. You cannot swipe the card at home on Amazon. So what the banks did was they said, okay, let's print another CVV number on the back of the card, which is different than the CVV on the magnetic stripe, and let's have the customer manually input that number so that we know that, okay, name, card number, CVV2, which is on the back of the card, let's authorize. So that's why it was introduced, and that is what is stored in the card not present type. So we'll mostly take a look at this scenario because that is what was exploited in all these dozen or 2 dozen breaches last year. So there has been a lot of talk about encrypting data in motion and data at rest. And again, don't read too much into this slide. It basically shows various different things that organizations do to encrypt the data while it's stored somewhere, and encrypt the data while it is sent from one place to another place. So we have SSL, and we have like various firewalls and VPNs and various other security mechanisms where data is encrypted at rest and in motion. But there is one important place where the data is not encrypted, and that's the place where these RAM scraping malware hit, and that's basically that's in the RAM. So when you swipe your card, before it is encrypted, it is still in clear text in the memory of the POS system, and that is where the RAM scraping malware basically scrapes sort of this RAM and gets your data. So let's look at how it works. Is this clear? I mean, because this is sort of the key point of although there are so many security things for encryption of data at rest or in motion, why is credit card data being stolen? Because in the RAM, before it is encrypted, someone has to read the data and someone has to encrypt it. So when I read the data and before I encrypt it, there is still like a few milliseconds, few CPU cycles where the data is still unencrypted. So what is the attack scenario? So let's take an example of real life attacks. Most of the attacks last year were because a lot of vendors, they basically outsource their credit card systems for updates and security and whatnot. And these outsourcing providers, they have remote desktop and running on these systems so that they don't need to come to patch the systems or to perform any sort of a maintenance on the systems. So what happened was a lot of these vendors still had the default username passwords or easily guessable usernames and passwords in the remote desktop configurations, and the attackers just came in like that. So getting inside the POS was very simple in some of the cases like remote desktop. In some other cases, people use their POS systems for things that they are not supposed to do. So I just mentioned that these are at the end of the day normal Windows or Linux systems. You can just get out of the POS application and check your Facebook update on it or your Twitter update on it, use it for email or whatever. And a lot of people used to do that, and that was also another point of attack where you just send an email, a phishing email, and if you happen to click it while you're on the POS system, the malware gets in. But the interesting thing is not how the malware gets in, but what it can do once it is in. So, okay, for a second, let's assume the malware got in. Second is customer swipes the card, and that's when the malware does its RAM scraping. So, what I mean by RAM scraping is that although the customer swipes his or her card, the credit card information is still in the POS process. So, I mean, all of us are engineers here, so we know that on any operating system there are different processes running, and one process, in at least modern operating systems, cannot really access data of any other process. So, although the data is in the POS process, the RAM, what the malware has to do is how does it get data from the POS process? So it does this technique called as RAM scraping, and that's what we'll take a look at in detail. So in the RAM scraping, what you do or what the malware does, and what exactly my malware here does, that will look in a few minutes, is it finds the POS process which will have credit card. Now, it doesn't have to do it, but it's an optimization, because as I mentioned that the data is in the POS process for only like a very short amount of time. And it's sort of a cat and mouse game, is who can get to the unencrypted data first. Can the malware get to the unencrypted data first, or can the POS process either encrypt that data or send it for authorization and throw it away? So a lot of times the POS process itself doesn't store that data on the POS terminal. So the credit card data is not, it's a huge responsibility. Everyone tries to not store the credit card data on their system. They try to just read it, send it for authorization, and then just discard that data. So as I said, it's sort of a cat and mouse game, is who gets to that data first. Either the malware gets to the data first, or the POS system encrypts it and sends it for authorization and removes it from its own process so that the malware cannot get it. So this step, which is done by the malware, is to be quicker. What it can do and what my homegrown malware here does is that it just basically looks at the top, let's say 20 vendors of POS systems and get characteristics of these POS processes. So there are like a certain calls, some of them I have listed here, that or APIs that you can call to enumerate processes, to open the modules in the processes and get the modules based in. This is the sequence that I followed, but you can follow like a few more sequences as well to find the process ID of the POS process. Another thing before I go till the end and you say, okay, where can I download it? Talk that with my colleagues and with my boss, and we concluded that we are not going to share the source code for the malware because it's still being sold for a pretty decent value in the market, and it's at least at that time it's just not too safe to give out the source code. So I have been forbidden to share the source code, but we'll look at it. So and in reality, if you are in reality, if you just look at these calls and do it yourself, I'm pretty sure you can write something like this by yourself. So at least those are the API calls that I use to find the POS process. Once you have the ID for the POS process, you know what's the process ID for the POS process. You elevate your privileges to something special. In this case, it is called as SE debug name or debug name privileges. So what that allows you to do is, if you are able, or if the malware is able to elevate its own privileges, then it can open other processes in the system memory, and it helps to, and it can aid in basically RAM scraping of those processes. So you elevate your privileges, certain APIs, again, open process token, lookup privilege values, adjust process tokens. These are, again, a lot of system calls going around here. And then the step 3 is pretty simple. If step 2 is successful, is if the malware was able to elevate its own privileges, then it can just open the POS process. It's a simple call open process for that. And it's like after step 2, it's just like as if the credit card number is handed out to you in a gift box. So I like that. I think. But anyway, step 3 is then do your RAM scraping. Basically what you do is you scrape the entire memory of the process, because you don't know. It's just zeros and ones. You are given just a piece of memory. How would you know where is the credit card number stored in that zeros and ones? Literally, you have like a big buffer given to you, a big buffer, and it has some binary data, and now you are trying to find where's the credit card number stored in that binary data. So that's the step 4 that the malware does, and we'll take a little detailed look at how that RAM scraping works. So some of the calls that at least I used were virtual query EX, read process memory, and there are some alternative calls and other ways that you can also use to achieve the same thing. Also, if you cannot elevate privileges here, there is an alternate path. There is a concept called as injecting your own DLL in other processes, and after which you can again go to step 3 and 4, but we will try to stick to simple stuff. So after basically getting access to this chunk of zeros and ones, the task is what is credit card data in that big chunk of just zeros and ones. So for optimization, what the malware does is it looks only for committed memory. So in a 32-bit system, or let's say most systems these days are 64-bit, but still you have a lot of virtual memory. In 32-bit system, process can have 4 GB of virtual memory. In 64-bit system, it can have like even it can access 64 GB. I'll check on that, but it can access a lot of memory or process. So what you do is you use certain flags, and these are the name of the flags that you will use in your calls to say that, hey, I don't need all the virtual memory for that process. I only need the memory that is committed. So everyone here sort of understands, right? Like in reality, you only have maybe 8 GB of RAM, but the process as a developer, when you are writing a program, you have access to like maybe 10 GB, 20 GB of RAM. And the way you can get more RAM than it is really present on the machine is because the operating system, whenever you access it, it reads it from the disk into the RAM and basically makes you feel as if you have a lot of memory, but if you don't use it for a long time, it again stores it on the disk. So that's why every process gets a feeling that I have a lot more memory than actually the physical memory on the box. So anyway, what the malware does is it tells that only give me memory that is committed. So that sort of reduces a lot of this big buffer that it has to search to a little bit of a smaller buffer. It ignores the memory that is part of the executable image. So executable image is executable image. I guess it's zeros and ones, which has the image of that executable exe or the com or whatever the executable image is. And that will not have credit card data because that has the source code, actually not source code, that has the binary code which corresponds to the source code. So that will not have credit card data. It remembers memory addresses for the next script. So we will take a look at how it finds the credit card number soon. But this is another optimization, and since we are talking about optimizations, is once it finds a certain location that credit card data is, it finds, the next one, every time you swipe the data, it sort of goes to that location first, because the probability of variables or that data being in that location is more. So imagine you have just written a simple program which takes input from the user. What is your name? You type, my name is Sam. And then that Sam goes into a variable which is allocated by the OS into a certain location. And there are a lot of new techniques, ASLR, and a lot of new techniques that operating systems do so that malware cannot predict this location. But it never, at least in my example, I saw that the card numbers were loaded into memory in very similar sort of addresses. And then you patch and match on track 1 and track 2 data. So finally, what we have seen in track 1 and track 2, which is basically, it started with this % sign, and then there was B, and then there was the caret, and then there was the account number. Now obviously you don't know what the credit card number is, but you know that it starts with this % B, and then 18-digit numbers, and again a caret, and then again your name. And then again, the malware will not know beforehand what is the name on the card, but it can say, okay, so give me any data which starts with this caret, %, it has this 19-digit number, it has this again caret, and then it has this alphanumeric, any alphanumeric characters for these many digits, and that you can easily do by regular expressions. So, I mean, if you are Perl, Python, PHP, any type of code, or regular expressions, so you can easily specify that, hey, give me the data which matches this pattern, and that's either you look for the track 1 data or the track 2 data. So pretty much that's how you or the malware gets to the credit card number by pattern matching. But after it gets the data, it has to still verify if it's a valid credit card number. And because although it's malware, they don't like false positives or false negatives. So what they do is they do something which is called as Lung algorithm. And now this isn't by no means a malware algorithm or anything. It's an algorithm to find which tells you if what the number that you have, the 19-digit number that you have, is really a credit card number or just ABC or just 1, 2, 3, 4, 5, 6, 7, 8, just any number. So what learn algorithm is, let's say this is your original number, your credit card number. What you do is you basically drop the last digit, you reverse the digits. So first digit 4 comes here, 5 comes here, this 5 goes there. So you reverse the digits, you multiply every odd digit by 10, so you don't multiply 5 with anything. So you multiply 5 with 2, that becomes 10. You don't multiply 8 with anything. Multiply 9 by 2, this 9 with nothing, this 8 with 2 again. So you do this, you subtract 9 to numbers which are over 9, and again, this may sound like a puzzle, but this is a well-documented algorithm. You can find it anywhere on the net. You subtract 9 to numbers that are over 9, so 10 became 1, it remained 8, 18 became 9, and then you again add all the numbers. And after you do that, if you get another number here, which is 85, and if you add this 85 plus 5 and the modulo mod 10 is 0, then that is a valid credit card number. So actually it's a good sort of a fun assignment to implement this, and you can just give it an input, put like 1, 2, 3, 4, 5, 6, 7, 8 till 19, and it should tell you that it's not a credit card number. You put other random numbers and it should say it's not a credit card number. Pick one of the cards in your pocket, put in that number, and it should say that yes, it is a credit card number. So that's learn algorithm. That's what the malware does to, at that point, make sure that you have that it's a valid credit card. And actually, the code looks really simple. So this is a quick and dirty C++ code that I wrote. Just a very few lines of code, and this function one will basically tell you if it's a credit card number or not. And this, yeah, it's very simple. So it's available. I can email you this. So I think it's available. It would be available in some other forms online as well. So that's what the malware does. Basically, it gets into the machine. It scrapes the RAM. It has a bunch of optimizations. It uses regular expressions to get to the credit card data, and uses learn algorithm to check if the card data is right or wrong. So time for a demo, and let's see, because this doesn't always work. So what I have here, and this is a little bit funny, I cannot see anything here, this screen is blank, so I'll have to go here and do this. So what I have is a credit card processing application, and again I don't want to target any vendor as such. This is a very nice vendor, a very big vendor, but a vendor who has already released patches and things like that. So if you are in this business, you will know immediately by the screen who this vendor is. What I have is a pretty simple credit card reader, a $15 reader. It's $15 because it can only read one way. If I swipe the other way, it won't read. If you pay like $10 more, and I was cheap enough not to do that, then you can slide it either way. So, so let's see. Let's pretend that I am at the cash register kiosk. What I do is so let's say I come to the store, I check in, let's say my name is Brian. So Brian is already in. Okay. So I clock in, so now I say, okay, now I'm at this terminal. Someone comes to the cash register, let's say this is a baseball store, so they buy a bunch of baseball hats and some baseball bats, and what I do is I scan them. So I don't have a scanner here, and a real baseball hat to scan. But what I'll do is I'll make the sale like this. So let's say they buy a baseball hat, and it's $11. All right, that's pretty cheap. It was not $11 when I bought it. Something. So they buy a bunch of stuff and then they give me their card as a credit, and this is where I would need a card. Good. So this is an expired card. You will see all the card numbers and CVV and everything if the demo works correctly on the screen. So they give me a card, and what I do is, I should have not been that cheap and bought the double-sided, but I think it is this side that I need to swipe. No. So they gave me a card and it reads the card. And at this point, now let's say if the malware is running in the background. So right now my malware here is not running in the background. This is your default directory where your compiler, compiles your code on Visual Studio. So what I'll do is I'll just run my application, which will do exactly what we just discussed. It will find the POS process. It will get the process ID, it will elevate its own privileges, it will open the process, it will scrape the RAM for those patterns and try to read track 1 and track 2 data from the card. Now again, remember, this is a separate program that I'm running, this is the malware, and the POS process is basically this process. So when I do this, actually it's pretty quick. It gave me all the data that was on the credit card. So it gave me the credit card number. So the first is the memory location where it found that data. So that's the memory location. Second is the credit card number, 40774 and 6004. It gave me the name. It gave me the expiry date. It gave me the service code. It gave me the CVV as well as the PVKI values. So it gave me basically everything. So this is all I need to do any sort of fraudulent charges on other cards, or I can just program. I mean, if I buy a $100 worth device, then I can use that to program blank cards as well. So I can just put this on a blank card and then I have a working credit card. I can just go in the gas station, swipe, buy. Question?
Is this using the elevation of privilege or the Yella injection?
So this, in this case, I did not have to do DLL injection. It uses the elevation of privileges.
And it doesn't prompt you even though you're elevating to debug?
It does not, yeah. So, interestingly enough, the process has this data stored twice in 2 different locations. So the second part is exactly the same as the first part, and it's just the way the variables work. So again, I don't know what is the logic behind the program, or it's just that all this data was in a variable, and somewhere that variable must have been string copied or copied into another variable or passed to a function by which another copy of that same variable was made. And basically that's how it gets the data. So another interesting aspect is, where's my, okay. So, although it's a baseball store, it's still asking for tips. I don't think anyone tips to the cashier. So if I say no tip or collect tip, whatever, let's say no tip. So then it sends the credit card data for authorization, and you see this yellow thing, it says that this is a demo account, no money is transferred. So otherwise every time I get the drop, there would be like this $30 transferred out of the card, or it will get rejected. So let me just, card has expired. Oh, so I'm using the old card, yeah, 9/14. So, okay guys, I really need unexpired card. This card was cancelled, but when I gave the talk first, it was not expired. So, which was in September, I guess. So anyway, I'm not going to use my unexpired card. So what I was going to tell you was that it is okay. I pressed cancel, but ordinarily the card would have gone through and it would have said, okay, the transaction is done. Now, interesting enough, if I run the same program again, the data is gone. It's no longer in memory. So that is what I was referring to. Is it's part of a cat and mouse game. Is who can get to that data first? Is the POS process able to encrypt the data and send it for authorization and remove it from its memory first, or is the malware? Can the malware get to that data first? Sometimes we observe that in some, as I said, this was a pretty well-written POS program, is that they send the data to authorization and then they zero out the variables where the data was stored. Because some other programs that we tested, that even though when you send the data for authorization, okay, the transaction is done, but you have to physically, the data is somewhere in the memory, and unless the POS program takes this effort of writing zeros to that location, the malware can still find it. I mean, the transaction is done, the customer is gone, but the POS process has to clear that variable and just write zeros to it. So this is a pretty good program after the transaction was either cancelled, which I did now, or if it had gone through, if the card had not expired. It does zero out the memory and then the malware cannot find it. So now it doesn't matter how many times I run, the data is gone. So yeah, basically that was the demo of how basically your RAM scraping malware steals credit card data. Last few things that we will end up with is how do we mitigate these issues. So how to what can good 5 minutes. So what can POS business owners do? So there are a lot of changes coming in the US now. First, what the business owners can do as of today is use the point of sale system only for its intended purpose. So, as I mentioned, the malware gets in by unintended use. So someone could be on the POS system, a cashier late at night, nothing is happening, they just temporarily close the POS system and maybe check their email, Facebook account, or some stuff like that. So we should, and it really happens in small mom and pop stores where you are the owner. We have even seen a lot of POS systems where that system was used not just as a POS but also as a payroll system, as an email server. And we're like, guys, this is a POS system, and I mean, although this is not a Target or this is a smaller shop, you still cannot use the POS system as your email server, as your things to check mail or play games, because it will get infected. Secure the remote management interfaces. A lot of breaches last year happened because the remote management interfaces were exposed. So secure them. Remote management software as RDP or VNC or any remote management software that you would be using. Use VPN and things like that. I mean, come on, we have already solved this problem a long time ago. It's just implementing that. Insider threats. So also 11% of the threats, again, this is 2014 data, which was for 2013. So where insider threats. So we had a lot of instances where someone just walks in at a 7-Eleven or some shop where the cashier is maybe a temporary person or doesn't have good intentions, just gives a USB stick and like $100 bill and says, just put this in and I'll collect it tomorrow. Or just put this in and you can give it back to me. We have seen some cases where that happens where the cashier thinks, hey, it's quick money, 100, 200 bucks just to insert something and give it back. But that has happened, which is basically what we call insider threats. Do best practices. So basically use run as in Windows. So have the entire OS run at lower privileges. When you are starting the POS process, just use run as so that the process gets all the privileges and all the other processes, including your malware, will not be able to elevate its privileges. So if you do that, then that could help. There are a lot of patches available. So patching is important. End of life, if your software is end of life, then please upgrade it. We still see a lot of older systems that are no longer supported, no security fixes are available for them, but they are still around there. And your normal vulnerability scanning, access control, auditing type of things. But the most important here is, and I think I rated them like that is because like the ones on the top are the most easiest to do or most cheapest to do, and as you go at the bottom, they become more expensive to do. Is enable end-to-end encryption hardware and software. So most people still use these $20, $30, or maybe $100 system, which is a little bit more robust. But still, this does not give end-to-end protection. So there are systems available where there is end-to-end protection, where the data is encrypted on the card reader. So that is a little bit more secure than the normal POS because the data is encrypted with some encryption token, and then that is passed to the POS terminal. So even if there is a POS malware running on your POS system, it will only get encrypted data. That is a little bit expensive though. The last thing is deploy smart cards, chip and pin, enable POS terminals. Now this is very easy for me to say, but it's a big issue because if the customers don't have a chip and pin card, then what are you going to do? You have to support the lowest common denominator. So you have to support magnetic card readers. Now, I think there is some law passed that all banks should issue chip and PIN cards in the US by the end of this year. And we'll see how that is rolled out and how is the deployment for it. Although we are not getting as secure as our friends across the pond in Europe when they have chip and PIN, I believe the law that is passed here is for chip and sign. So there is a chip on the card, but you don't need to enter a PIN, you just have to sign. So it's like halfway secure. And it's not that we don't have the technology, it's just that there is enormous cost in upgrading all the terminals. So just imagine all the places where they accept credit cards. If you have to upgrade all those terminals, that is an enormous amount of effort and energy and money. And and it used to be that people used to calculate risk in this way, that okay, how much is the POS breach going to cost me? Okay, so many million. And how much is it going to take to upgrade all these terminals? And well, okay, even if I assume the worst case scenario, I'm still profitable, so let's not do that. But that's changing because as we saw last year, there were a lot of breaches, so people just didn't lose money, but they also lost sort of their brand name. So I think that will change, but it's like a chicken and egg thing. Is unless everyone has a chip and pin card, the terminals cannot be chip and pin only. But or if the terminals are chip and pin, then and if the customers don't have that type of card, then you cannot accept that card. Ideally, you should have both the terminals. Some suggestion for POS software vendors is restrict unencrypted data in memory. So try to process the data as fast as you can. Also use built-in encryption supported by various application frameworks. So various applications they allow is built-in encryption because we have seen homegrown encryption done by a lot of POS vendors, and encryption is such a thing that if you are developing the software, don't do any homegrown encryption. Always rely on something that is built in, that is tested. Even those well-tested libraries have vulnerabilities, so don't rely on yourself for encryption. Always use some libraries that really exist. So with that, what can credit card users do? Audience participation. Do you have any idea?
Pay cash.
Pay cash. That's the only suggestion, or that's the only thing that I think I can do as a user, because as a user there is nothing really I can do in here. I cannot go and upgrade their POS terminals. I cannot put a chip on my card and say, hey, my card has a chip now. So really, other than paying cash, there is nothing really much we can do. So with that, that's my Twitter handle. If you have any questions about the software, about the malware, about code, or any question about POS, feel free to ask me, and I'll open it up for question and answer.
What is it about?
So these are pretty, those are very good alternatives for credit cards, because their card number is never transferred. I haven't looked at it in detail or tried to break it, but from at least the design of it, you have basically only like a one-time number, or like a token is passed, and if that is stolen, that's a one-time token. So I think all the newer mechanisms are pretty good, but again, it's how quickly and how widely it is adopted. But again, being said that, I haven't really looked at it in the really details or tried to break it or anything like that. But looks promising, definitely. Any other questions? Well, all right. Thank you for your time.